Imagine for a moment that you're a professional mathematician and you've just made some amazing new discovery. Let's say you've discovered some unusual formula that's true for all numbers. Filled with excitement, you call up one of your mathematician friends. "Hey Fred, guess what I just discovered?" You go on to explain your formula to your friend. Well, he pauses and says, "How do you know it's true?" You say, "Well, I tried it for the number 1 and the number 2 and the number 3, and it seemed to work, so I'm pretty sure it works for all numbers." Now, do you think Fred would find that convincing? Would he trust the formula based on that explanation? No, of course not. There's still plenty of numbers, an infinite number of numbers, in fact, that you haven't tried yet. Now, this is basically what mathematicians do all day. They explore abstract models, discover amazing new truths, and then they want to go tell their friends about their discoveries. But if they can't convince their friends that what they've discovered is true, it's probably not much use. Because of this, mathematicians have spent a lot of time thinking about the question of what makes an explanation convincing. A totally airtight explanation is called a proof. Now let's think about this in the context of chocolate fix. Let's say I've just been working on a really hard chocolate fix puzzle and I finally cracked it and got the solution. Now I'm really excited, so I call up my friend Bill and I say, "Hey look, I solved this puzzle." Now to convince him I solved the puzzle, I need to show him that I can find each clue pattern somewhere in the grid. So I look here, here's the full grid pattern, and does it work? Dark, pink square, pink triangle, light, pink triangle, light square, dark triangle. It works. And the partial clue is found up here in this area, and there's the square that the partial clue is talking about. So both clue patterns can be found in the grid, so I've definitely solved it. Should he be convinced? Yes, absolutely. That's all you need to do to confirm you've found a solution, is to show that you've found each pattern somewhere in the grid. And a lot of things in math are like this. There are things in math that are easier to check the answer than to find the answer to begin with. And that's fine. But let's think about this a little harder. What if Bill says to me, "Okay, I accept that that's a solution, but how do you know it's the only solution?" Now this is a little trickier. Showing that each clue pattern can be found somewhere in the grid does nothing to convince him that this is the only solution. The only way I can convince him that I have found the one and only solution is to explain my reasoning. I have to demonstrate that I have considered every possible alternative, and this is the only one that worked. Now you've already seen in previous videos how I go about finding the solution to these sorts of puzzles. But let's see if I can turn this into a really convincing explanation that this is the only solution to this puzzle. Now to do that, I'm going to start from scratch, and I'm going to work through the solving process, and I'm going to try to convince you that I am considering every possible alternative along the way. Well, the full grid clue is pretty straightforward. I know exactly where that goes, so I just have to copy that information in. Now it's time for me to consider the partial clue. The partial clue looks like physically it could fit either here or here. Now this puzzle is a little trickier than the puzzles you looked at last week, because last week, most of those puzzles, it was pretty clear where that partial clue needed to go. On this one, at first glance, it seems like it could go either spot. Maybe the square could go here, maybe the square could go here. Now some of you may already see that one of these leads to a problem. But for those of you that don't, that's okay. It's my responsibility as the explainer to convince you what happens either way you place this partial clue. Now I have a trick to make sure that I'm carefully considering all the possible alternatives. I call it a tree diagram. Now I'll be going a lot more into detail about tree diagrams in future weeks, but right now I just want to give you a little quick preview of how that works. So just to be clear, I'm not talking about this kind of tree. When I talk about a tree diagram, it's more like a kind of decision map, where every time you come to a fork in the road, you make a picture of all the branches you could follow. By convention, we usually draw the picture starting at the top and branching out as we go down. So this is a tree picture of the decision we're facing right now. And one of the reasons I like tree diagrams is it's really easy to see what is the question we're asking. We want to know where can clue 2 go, that's the partial clue, and we can see all the possible answers. It can go here or here. Looking at this tree picture, there's no mistaking what all the options are. So let's consider this possibility first. So if the clue goes here, that means this has to be a square. Now do you see what the problem is? Now that we've actually put the square in, it's a little easier to see. The problem is that we have 2 light squares in our grid, and we know that's impossible. This is what's called a contradiction. A contradiction is when you make a choice and you realize it's impossible. There's no way that could happen. So it's safe to back up and try the other choice, and you know that's all that's left. Let's record this information in the tree diagram. So what did I do? I figured out that if the square went there, then there's 2 light squares, and that's obviously bad. Okay, now we can go back and take a look at the other possibility. So first I'm going to get rid of this and put it back the way it looked before. So this is where it looked before I made that choice, and now I'm going to consider the possibility that this clue goes up here, which would mean that a square goes here. Now we solve it using the techniques we've looked at before. There's only 1 pink left to go here. There's, let's see, only 1 square left to go here and 1 dark piece to go here. This is the last triangle, and that's the last light piece. So there you have it. This is the solution, and because you saw that I explored all the alternatives, you know this is the only solution. Now I'm going to go back and record this on the tree. Now hopefully between my verbal explanation and between this tree picture, it should be really clear that this is the only solution, and I hope I convinced you. Now it's your turn. I've made up for you a puzzle workbook, and just like last week, I want you to go through and solve the puzzles and write your answers on the solution worksheet so that someone can check them. But this week, sometime before the end of class, I want you to pick out one puzzle that you feel you understand really well, and I want you to explain it to someone and explain how you know it's the only answer. You can explain it to your partner or to your teacher, or better yet, if someone in the room has a video camera, go ahead and explain it for the camera if your teacher says it's okay. Now you don't have to use the tree picture that I was just showing. That was just a preview of something we're going to be looking at in future lessons. Right now, I just want you to talk through your reasoning process and explain your solution using your chocolate fix set for demonstration purposes. The most important thing is if you discover that there's a choice about where that partial clue goes, I want you to explain what happens with each of those choices. So for example, if it turns out that some of those placements are impossible, that's fine. Just make sure you explain how you know it's impossible. Most importantly, have fun.